Astronomers interested in the age and the size of the universe look for answers in the light which reaches Earth from space. Historically, they've been hampered by the fact that only a narrow slice of the spectrum of light is visible to the human eye, and that any telescope on Earth only sees light after it's been distorted by passing through the atmosphere, if it gets through at all. To address these issues, NASA embarked on the Great Observatories program, a series of telescopes orbiting above the atmosphere, which together gather data from across the spectrum.
If you can study a wide part of the spectrum, you can get more information about the objects that populate the universe. And technically speaking, we cannot have a telescope that can study objects in the gamma ray part of the spectrum and at the same time the infrared, because these are completely different technologies. The technology not only of the detectors at the focus of the telescope, but all the imaging system is of a different nature. So we cannot have a telescope that observes the total spectrum of radiation.
The first element of the program to be put in orbit, focusing on visible light, was the Hubble Space Telescope, delivered by a crew of astronauts in April 1990. But within months, scientists discovered that an imperfection in the curvature of the 5-story tall, 12-ton telescope's main reflector prevented it from achieving sharp focus. The solution was corrective lenses, installed in 1993 by a team of spacewalking astronauts. The robot arm operator on that mission was astronaut Claude Nicollier, now on his second Hubble mission, but this time as a spacewalker. The on-orbit tune-ups, including the 1997 mission on which the STS-103 payload commander, Steve Smith, conducted 3 spacewalks, have all been planned around Hubble's modular design, which simplifies the tasks for astronauts wearing bulky spacesuits.
The shuttle has a robotic arm built in Canada, the RMS we call it, remote manipulator system, and that arm allows us to take one crew member and move him or her around and take boxes out of the thing and put boxes back in, while the other crew member can be tethered to the arm or to him and loosely moving around, or independently moving from the shuttle's cargo bay, up to the work site. And this harmony, this choreography between the operator of the arm, who's in the on the shuttle flight deck, and the 2 crew members out there, can really achieve an enormous amount of physical labor reconfiguration work very quickly.
The new optics installed on the first servicing mission dramatically improved the images Hubble was able to return to scientists on the ground. In the years since then, Hubble has provided astronomers with views of the cosmos they'd only imagined to be possible. From close-ups of our neighbors in the solar system, like this view of Mars, to seeing neighboring stars self-destruct in a supernova explosion, to views of stars being born, like this peek into a nebula in the constellation Orion. And heading into its second decade, Hubble also helped complete one of its major goals by narrowing down a measurement of Hubble's constant, the rate of expansion of the universe, to establish the age of the universe, approximately 12 billion years old. The second telescope in the Great Observatories program reached Earth orbit in 1991. The Compton Gamma Ray Observatory, like the Hubble before it, was deployed by a shuttle crew, who proved their value by conducting an unscheduled spacewalk to manually deploy the telescope's high-gain antenna, which had resisted computer commands to move into proper position. The instruments on the Compton Observatory measure the strength of gamma-ray emissions, which originate from high-energy phenomena like solar flares, pulsars, supernova explosions, and the edges of black holes. Observing in this portion of the spectrum, Compton was focused in for a number of views of the center of our galaxy, widened its scope for views of the entire sky, and discovered a new class of active galaxies known as gamma-ray blazers. The mission of the third Great Observatory is just beginning. The Chandra X-ray Observatory was brought to orbit by a shuttle crew this past July and has just begun returning data. Chandra complements Hubble and Compton by measuring not only the position, but the energy level of X-rays reaching its science instruments. Scientists study that data to understand how the energy was produced and what produced it. A supernova, for example. A remnant of a supernova 190,000 light-years away from Earth. Or a 6-billion-year-old quasar radiating the power of 10 trillion suns. The fourth telescope in the Great Observatories program will concentrate on the infrared part of the spectrum. The Space Infrared Telescope Facility, still under development, is to study low-temperature environments, such as interstellar clouds where stars are forming, and the icy surfaces of planetary satellites and asteroids. SIRTIF is targeted for launch on an expendable rocket in late 2001.